There's also a prism up here that the survey gun uses. It's a total station that gives us the ability to track the rover with millimeter or centimeter accuracy, depending on how far away the rover is. It's automatic and gives a great baseline for comparing path reconstructions to. Now, one effect that I won't get into too much detail, but it is noticeable, is the sway caused by this mast, because it is roughly a meter, maybe it was a meter and a half off the ground, and the rover was driven over a lot of slopes, rocks, and bumpy ground, so the mast was moving substantially, and it was reflected in the ground truth data. You'll actually see some subtle effects of that in the video later. The other technique that had to be done or performed on this data was to correct for the proximity effect as the rover approached the artificial sun light source. Because the light is not infinitely away, the closer the rover gets to it, the sun appears to move relative to the rover. As the rover drives close, the elevation of the artificial light moves upwards, which doesn't affect the heading until the rover rotates or pitches and rolls. And also when the rover moves perpendicular, as in this maneuvering location here, the relative bearing to the sun appears to change when the rover's heading is not changing. So we compensated for that simply by finding what the rover's offsets were in coordinate space to the light source. We surveyed the light source with the survey equipment. And so this is the effect here. This is before the compensation for the proximity effect, and this is afterwards. So you can see that here, this path reconstruction in purple is the path reconstruction created from the sun sensor. The blue is the ground truth path that was actually measured. The black line is the path reconstruction performed with the inertial measurement unit using its yaw gyro to integrate a relative heading. And the green is the path that's been reconstructed using just wheel odometry alone. All of these paths, the green, the black, the IMU, the purple, solar compass, all use the wheel odometry data as their source of forward displacement information. But each one uses a different source of heading information. So in the original equation, they all use a different theta, but they're all using the same exact distances. So once again, you can see here that all the headings are parallel to the ground truth after the compensation for the proximity.
Can you just remind me what the different colors mean?
Sure, yeah. The green right here is the wheel odometry path reconstruction. The blue line is the ground truth measured path. Black is the path reconstruction that's a combination of the inertial measurement units heading and ground truth, and wheel odometry displacement. And then the purple is the solar compass path reconstruction using only the solar compass's heading and the wheel odometry displacement. And again, you can see, located relative to the light source. So this video shows through time the recreation of these paths played back at much higher than real time to give you a sense for how these paths are affected by the relative error. You can see there's a little wiggle in the point. Each one of these is this blue is the ground truth, so that's the actual position of the rover at time. And the other three lines are recreations of that path. So here you can see very quickly that the green, which is the wheel odometry, diverges, and its position error grows very, very quickly due to early blunders in the heading, incremental heading. You can see that the black line, the IMU, its shape is very close to the ground truth shape, but it slowly drifts away because of the relative nature of the heading gyro, and there's no absolute references for heading. The purple trace, the solar compass, is following the ground in heading, and it is off a little bit, mostly caused by errors in the wheel odometry. Because it was, there are better wheel odometry systems out there, but it was enough for the test. So here you can see that this is that end location. This is the plot of the position error. This is the difference between the end of the path where the rover is located along as the distance traveled. So that what you just saw was about 300 meters of driving. And this shows how the error accumulated over time for each one of the reconstructions relative to the ground truth position that the rover followed for path. Again, the colors are the same here. Green is the wheel odometry reconstruction. Black is the inertial measurement unit with wheel odometry. And purple is the solar compass with wheel odometry. And so we can see here that it's predicted in the literature that the path reconstruction with an IMU typically has a superlinear error that grows, and what other researchers have seen with the sun compass is that it follows a nearly linear error growth. Also, this shows the percentages. For this trek, it was a 3% total error for the solar compass and a 12.9% for the IMU. And earlier, several of the solar compass treks from the Canadian research have very similar error level when they combine the solar compass with visual odometry. So in this case, we were able to get a very similar result using only a solar compass and wheel odometry, which is typically less accurate than the visual odometry methods. They're using a stereo pair camera. This shows the real crux of the reconstruction methods, which is the heading estimate. And again, the colors are the same. Green is the wheel odometry, and you can see that this diverges from the other measurements drastically throughout the entire trek. Here on the left, this is in radians, with 0 starting right in the middle. And this runs from the beginning of the test to the end of the test, just as was displayed in the video earlier. And to notice is that the purple, which is the solar compass, gradually, at distance, the IMU drifts away from the solar compass. And this right here was a bad data point that snuck in here again. That was due to a false image. So here you can see the IMU, and all three of them started exactly the same heading, and you can see the gradual drift that accumulates because of the relative heading integration.
Your time on the x-axis seems to be frozen.
Well, so this was not converted back into human readable time. This is in the Unix epoch time in seconds since 1970, so it's a 10 to the 9th number. So to sum up the contributions here, the absolute bearing from the sun was shown to substantially increase the accuracy of the route determination using only wheel odometry and simple measurements. And the solar compass was able to outperform the IMU that we used, which was a mid-grade. It wasn't a tactical grade IMU, but it was a fairly decent inertial measurement unit as far as they go. And this also shows that the solar compass could operate alone or in concert with a heading gyro. So as long as you have an accelerometer, a 3-axis accelerometer, you wouldn't necessarily need gyroscopic sensors to use the solar compass, and you could get results similar to a gyroscopic heading in terms of temporal resolution. Most of the other research with the sun sensor didn't take images at a high rate relative to the rover's rate of travel. And so then the solar compass measurements were used as tie points for the heading. And integral methods such as wheel odometry or or gyroscopic measurements are used in between the spaced out solar compass measurements. We were able to do it, or this research was able to do, like I said, with much faster shots of the sun, and more or less replace the heading gyroscope with just the solar compass. And that was as a result of using underexposed images instead of solar filters. That was part of that. Future work for the solar compass, one would be a miniaturization of the system. Right now, using just commercial off-the-shelf parts, it's a relatively large system, about the size of a lunchbox altogether, including the computer to process all of the information. That could be done with something the size of a cell phone fairly easily. The space qualification of a system like this would be very useful for rovers in the future. Like I said, the field of view of this type of sensor using typical fisheye lenses that are relatively small, about quarter diameter sized, and they go up to there are ones that are over 200 degrees field of view are common. So it's over 2 times the field of view you would typically get with satellite grade sun compasses or sun sensors. Extending the autonomy for operating in the sun days apart from communication. Tests like that could be possible with this. Like I said, they may even be possible just with wheel odometry and just with the solar compass without a very expensive high-grade gyroscope for heading measurements. It would also enable ordinal navigation, like for instance to go north or go east or follow a certain bearing. That information could be performed with very high likelihood if you're using the absolute reference from the solar sensor. One thing I didn't mention earlier was probably even terrestrially, there's big advantages to the solar compass. They were used for survey instruments in the 1850s until the 1970s as a standard measure when magnetic compasses were not working due to ferrous anomalies in the ground, particularly measuring iron or surveying iron ore deposits. And they were rather large